Hello and welcome. This is also a mixing problem with a twist. On the left chamber, we have a mixture of hydrogen and CO2, and on the right chamber, we have pure oxygen. If part A and part B were both pure gases, then we could use the binary mixture model. But however, now we have a mixture on the left chamber. So the correct model to use will be NPG or an NIG model, where any number of gases can be present. And because specific heats are constant, we will use the NPG model. The conditions are supplied in each tank, and we are asked to find the final temperature and final pressure as well as entropy generation. I have solved a similar problem involving pure gases, so let's expand on that idea. So we'll go and start the suitable test step, closed system, generic branch, mixing process. If two gases were pure, we would have picked PG plus PG or IG plus IG, or with the same gas mixing, we would have picked up a pure gas model, but now we'll pick NPG model. This is going to allow us to have the final mixture made of 3 different species. Okay, so let's begin. Mixture A we'll call, that's our left chamber, 50% hydrogen, 50% CO2 by volume. So the proportions are given in mass. In this case, we know the percent by volume. So we know hydrogen is 50%, we have 50% volume, and CO2 is 50%. So in many different ways, you can assign the proportion of a mixture. Remember, these are just proportion, not absolute amount at all. So this will be discounted in the final analysis. The mass fraction and mole fraction are what matters from this mixture. So notice that the mass fraction we are going to use, so let me write that down, because to compose mixture C, we'll need this mass fraction. So I'm writing it down on the side, which I will need while composing mixture C. Notice that, okay, so now let's go find mixture B, which is pure oxygen. So it doesn't matter it's kg or kilomole or whatever here. So mixture B is pure O2. So we just click on oxygen and add, this is our pure oxygen. Now to calculate mixture C, obviously we'll need mass of hydrogen or proportion of hydrogen, CO2, and oxygen. So for that, we only know the mass fraction in chamber A. So maybe we should find the mass of state 1 and state 2 first. For which state 1 is mixture A, the mixture that we got, CO2 plus H2, and the information supplied are 200 kPa and 20 degree C. Also, the volume is supplied to be 2 meter cube. So there we go, the mass of state 1 or the mixture A has been calculated. For mixture B, for state 2, make sure you select mixture B here, otherwise the problem will be totally incorrect. For state 2, we have pure oxygen, which we are calling it mixture B. So given data are 600 kPa, this is my tank 2, 100 degrees Celsius, or tank B, and volume is 0.2 cube, and that calculates the complete state. So mixture B is known. Now that we know the mass of state 1 and state 2, we can compose mixture C. We could go back here and enter the proportion of these 3 components, but to make it easier, I'll go to the IO panel and declare some secondary variable. So where the proportion of hydrogen, CO2, and oxygen in state 3 or mixture C can be found here. So mass of hydrogen would be what? It's mass of state 1 times the mass fraction of hydrogen in state 1, which is mixture A. And I noted that number down, 0.04379. So this is mass of hydrogen, or its proportion at least, in mixture C, and mass of CO2 in mixture C can be obtained similarly. We can say that equals oops, we can say that is equal m1 times mass fraction of CO2 or m1 minus mass of hydrogen, because there is only hydrogen and CO2 in mixture A. By the way, the calculated values appear below, so that means we have done it correctly. Mass of oxygen is simply m2. So now that we know this, we have defined these variables, it's easier to, instead of entering equations here directly, we can just say mass of oxygen equals MO2. Mass of hydrogen is equals M hydrogen, and CO2 is okay. When we add them, the proportions are correct now, and we composed mixture C here. We go back to the state panel, and this time we can calculate state 3, at least partially, because now we know it's mixture C. Remember, this is a very important step to make sure that C, yes, state 2 is mixture B, state 1 is mixture A, so state 3 should be mixture C. What we know about this final state is mass must be conserved, M1 plus M2, and the volume must be total volume. But that's not sufficient to calculate the state, obviously. P3 and T3 are our desired unknown. So we go to the process panel and try to solve the energy equation. It's already set up for a mixing problem with a composite beginning state BA and BB. So you can see 1 and 2 are mixture A and B, and the final mixture is just state 3, mixture C. We also know there is no heat transfer and there is no boundary work. The system doesn't change its volume, and other types of work, which is electrical and shaft, they are 0. So now the energy equation can be solved because Q is 0, W is 0. These terms are known, these terms are known, and even the final mass is known. So final specific energy can be calculated and posted back in state 3. So if I do a calculate here and go back there, yes, the energy has been calculated and posted, and now a calculate button should bring us the final pressure and temperature, and in the IO panel, in the process panel, the entropy should also have been calculated. So the problem has been solved.